Hello again. Today we're still going to be talking about hypothesis testing in Chapter 7 of the Stats and Mechanics Edexcel Pearson book on mathematics. So without further ado, let's get right into it today and keep it as simple as we can. Here's 4 warm-up questions. So either copy these out or get them printed off if you're lucky enough to have a printer. Pause the video now, try them, press play when you're ready to see the solutions. Okay, without further ado, here's the solutions, starting with question 1. For question 1, we're given this distribution, which is binomially distributed, 10 trials, probability of success 0.3. We need to find and label a critical region for a 2% significance level. So if you have a look at the lower tail, the lower end, already we're above 2%, because 0.0282 is above 0.02. And so our significance level can't be down here. It must be up at the higher end. And so we're wanting to find the value which, when we do 1 minus this number, it becomes less than 0.02. So for example, if we had a look at where it goes above 0.98, we're drawn to x being equal to 6. So that tells us that the probability of x being equal to or greater than 6, well, that's 1 minus the probability of x being up to and including 5. So that's 1 minus 0.9526. 0.9526. Yep, that's right. Just making sure I'm reading it correctly. And that gives us 0.0474. Now that is greater than 0.02. And so that's not significant yet. But if you should try x being equal to or greater than 7, which is 1 minus the probability of x being less than or equal to 6, what we get here is 1 minus 0.9894, which would give us 0.0106, and that is the first value that gives us a value of less than 2%. Therefore, x being equal to 7 is our critical value. Our critical region is therefore x being equal or greater than 7. So labelling the critical region, we have to do this, to label it. And we can also state it as well. So we're going to write it down. So for critical region, is x being equal to or greater than 7 all the way up to the maximum it can be, which is 10, because there's only 10 trials. Question 2. We have a magazine claiming that 30% of its subscribers are under the age of 30. Now, this editor of the magazine suspects this figure may actually be higher, so she employs a statistician to test this claim. So given that the statistician takes a sample size of 10 from a list of subscribers, we need to describe a suitable sampling technique to collect the data. Now, 10 isn't a big sample, so to make it completely fair and unbiased, the main thing we need to do here is to make sure the sample is random. And so what we need here is a random sample. I'm going to explain one method which could give us a random sample. So we're going to do a random sample. Now what we could do is assign each subscriber in this list a number. It does mention a list. Where does it say list? There. So assign each subscriber in the list a number. Let's say from 1 to n, where n is the number of subscribers in the list. Now what we could do is generate some random numbers. So use a random number generator to generate distinct numbers between 1 and n inclusive. And if we get any repeats, they need to be ignored. So the idea of this is we number all these people in the list from 1 to n. Let's say someone is number 273, and if this random number generator generates 273, we pick that numbered person. So we do that 10 times to get 10 randomly picked people. Part B, it then says to write down 2 suitable hypotheses to test this claim. So what we need to do here is assume that by default that the proportion of subscribers under the age of 30 is 30%. So our null hypothesis is to assume that p equals 0.3, whereas the alternate hypothesis is that p actually might be greater than 0.3. There might be more than 30% of subscribers that are under 30. So we need to just mention what p is, where p is the proportion of subscribers under 30. Warm-up question 3. So using what we had from question 2, the statistician found that 7 out of 10 people surveyed were below the age of 30. Testing at 2% significance, use your answers to question 1 and 2, this is a big hint here, to write a conclusion about these findings. Well, from question 1, we saw that the critical region was x being greater than or equal to 7. So therefore, if this test statistic comes out as being equal to 7, that's in the critical region. And anything in the critical region forces us to reject H0. So therefore, we reject H0, and we therefore conclude that the proportion of readers that are under 30 years old, or proportion of subscribers, I shouldn't say readers, I'm assuming these are readers, I think they probably are, proportion of subscribers under the age of 30 is looking like it's greater than 30%. Finally, question 4, calculus corner, which is going to be a permanent fixture. Calculate the area of the shaded region. And so we've got here this curve, which is y equals x brackets x squared minus 4. We should know that now that to calculate the region bounded between the x-axis and a curve, it's the integral between the boundaries, which in this case is between minus 2 at the lower end and 0 at the higher end, of this curve with respect to x. So if we expand this out, x multiplied by x squared gives us x cubed, and x multiplied by minus 4 gives us minus 4x. And so we need to integrate this function with respect to x. And you should know by now that when we do this, we increase the power of x by 1 and divide through by the new power. So x cubed becomes x to the power 4, and we divide through by 4. So we have a quarter x to the power 4, whereas over here, we'd then have minus 4x squared divided by 2, which is minus 2x squared. And we integrate this between the limits of minus 2 and 0. If we were to input 0 into this expression, that obviously will just give us 0. Then we subtract the lower limit, which is a quarter, minus 2 to the power 4, minus 2 lots of minus 2 squared. So if we were to try this on our calculator, doing it the long way, if you're thinking, well, what does he mean by the long way, what's the easier way? I'll show you in a second. First of all, we have 0 minus, then in brackets, a quarter, brackets, minus 2 to the power 4, minus 2, in brackets, minus 2 squared, and that gives us an area of exactly 4. So the easier way, the cheating way, the naughty way, is to use the integral function on the calculator, which is this button here. Type in our limits. So the lower limit is minus 2, the upper limit is 0, and we can type in the function exactly as it appears. So alpha x, brackets, alpha x squared, minus 4, close brackets, press equals. There we go, we get 4. It couldn't be easier. So the main course for this lesson is how to perform a one-tailed test. So I'm going to talk you through a step-by-step procedure for doing so, and I'm going to show an example, again using this step-by-step procedure. So first of all, what we need to do. To carry out a one-tailed test, we need to formulate a model for the test statistic. We then need to identify suitable null and alternative hypotheses. Afterwards, we then need to calculate the probability, which is called the p-value, of the test statistic taking that particular observed value, either higher than that observed value, equal or higher to, or equal or lower than, assuming, of course, as ever, that the null hypothesis is true. We then compare that to the significance level of the test, and then we have to write a conclusion in context of the question itself. And alternatively, what we could do is find the critical region first, and then compare afterwards the observed value of a test statistic against that critical region to see if it falls inside the critical region or outside. So, first of all, we've got a worked example here about the treatment for a particular disease, which has 45% success, or is claimed to have anyway. A medical research charity has developed a new treatment which has been successful with 13 out of 20 patients. The charity claims that this new treatment demonstrates an improvement on the standard treatment. So let's test at 5% significance the claim by the charity using this strategy from before. So first of all, we need to formulate a model for the test statistic. The easiest test statistic to use, I would say, would be the number of patients in the trial for whom the drug was successful. And then our P, the probability, we can define as the probability of success for each patient. In other words, if the treatment's successful for the patient. So we could have something along this lines in blue. So the distribution will be binomial, 20 patients, and P is the probability of a successful treatment. The null hypothesis would be to assume that the probability of success is 0.45, whereas the alternative hypothesis would be that this new treatment has improved this 0.45 figure. So our H0 and H1, I'd suggest we could do these here. H0, P equals 0.45, H1, P is greater than 0.45. Next, we need to calculate the probability of the test statistic taking that observed value. And so our test statistic here is 13 out of 20. And so what was the odds of having 13 or more patients for which this was a success? Well, this is where we bust out the class whiz. How to get the correct mode? We press menu, 7, scroll down to CD, press 1, press 2 for variable. So what we want to do here is to find this probability of being 13 or higher. Well, first of all, we need to remember this is 1 minus the probability of having 0, 1, 2, 3, 4, all the way up to 12 patients which it's successful for. Whatever's left will be the probability of having 13 or more. So that's 1 minus, let's work this out now. So x, 12 out of 20 patients, 20 trials, our probability, assuming H0 to be true, is 0.45. This gives us 0.94196, so to 4 decimal places, 0.9420. And that gives us 0.0580. So that's the third bullet point done there. We now compare this to the actual significance level. Our significance level was 5%, which is 0.05. This is over 0.05. And so because this is over 0.05, there's not enough evidence to reject H0. And so because we're not going to reject H0, it's not quite that unlikely enough. We have to conclude, therefore, that this new treatment is probably no better than the old one. There's not enough evidence to suggest otherwise. And so the new drug is no better than the old one, according to the evidence we have in front of us. Now, we did mention that we could have found the critical region first and compared the observed value to that. So let's have a look at this alternative method. So finding the critical region. And so x being 13 or greater wasn't. So let's just try going up slightly. So let's try this figure here. So what's the probability of x being 14 or greater? Well, that would be 1 minus the probability of x being up to and including 13. So using the class whiz, the probability of x being up to and including 13 is 0.9786. 0.9786. And so that's going to be 0.0214, and that is the first value, which is less than 5%. So that tells us that our critical value is x being 14. So the critical region is between 14 and 20. Where 20 is the maximum it could possibly be. We now compare to see what our test statistic was. Our test statistic came out as being 13. So x equals 13 is not in the critical region. Therefore, we accept H0. So that's just a different way of doing it. And obviously the same result. So that's all it is really. The next is over to you to just try and get these ideas solidified by doing some old-fashioned practice. If you turn to page 106, attempt exercise 7C, these suggested questions. Do your best, self-assess using the answers at the back of the book. If you're getting stuck, please do email me and check, or leave a comment in the comments section. Don't just not try the questions or assume it's going to be okay if you leave it alone. It won't be, so do get in touch. Once again, thanks for listening, and I'll see you again soon, or you'll hear from me in the next video. Thanks, see you soon.